All right. So given these graphs, what are you thinking? How does the displacement of object 1 compare to object 2? We're saying, I don't want that there. We're saying now that the displacement of object 1 is less than that of object 2. Okay, that's 17 of you. 3 think they're the same. 2 think that object 1 is a greater displacement than object 2. So let's peel the question back to that fundamentally. What do you think the displacement of object 1 is? The displacement of object 1 is blank meters, and I'm going to turn this into a number slide. Okay. What do you think the displacement of object 1 is? What's up with Thayer? Is he out smoking cigarettes to get ready for the cross-country meet? All right. What are we saying over here? Boop. Boop. All right, so here's my number line. I got somebody that thinks it's 0, but generally speaking, most people are getting 4 for that. Got a couple zeros, got a 12. Most folks are thinking 4. So one of you 4s, have at us. What's your methodology? How'd you arrive at 4 meters for the displacement? Yo, Paul. Sorry, what'd you get?
Peter.
Peter, damn it, there we go.
So the way I got it for is, so this is a velocity, so velocity is on the y-axis, time is on the x-axis. So from the second 1 to 2, it has a velocity of 2 units per second. So.
Oh shoot! Sorry, I screwed that up. Amongst other things. All right. All right, Peter, have at us.
All right. So it has a velocity. It travels 2 meters between the time intervals of 1 second and 2 seconds. During 2 to 3, it's stopped. It doesn't have any velocity. And then from 3 to 5, it has velocity of 1 meter a second. So for a total time of 2 seconds, so 1 times 2 is 2 meters of travel. So n equals 2 is 4.
Okay. Anybody else have a different way of explaining that? Arrive at the same answer, 4 meters, or that's what everybody did? That's what everybody did? All right. Let's see who can be first in with actually I want to do it this way. Boop. All right, let's see who can be first in here with the correct displacement for that one. What do you get? All right, first in was Ted Theodore Wilbur with an answer of 8, and then a whole bunch of other people. Ted, how'd you get 8 meters for this?
I counted the squares.
All right, there we go. So counted the squares, got 8. Why does that work here?
Me?
Ted, yeah. Or does it work here? Because what's a square worth?
Of 1 meter.
Okay. Did it wrong. Come on. So I look at one. It's not really a square, Mr. Harding. Okay, rectangle here. And if we pull that out, that is how tall, Ted? I don't want to change the color of it. Come on.
1 meter per second by 1 second.
Right? These are weird dimensions. 1 meter per second by 1 second. Okay? That's the dimensions for this box. So we work that out, and 1 meter per second times, come on, buddy, times 1 second equals, seconds cancel, 1 meter. Okay? So each block is worth 1 meter. 1, 2, 3, 4, 5, 6, 7, 8. Okay? So 8 meters. Whoop, I don't want to be doing that. Boop, boop, boop. There we go. So if I go back to the original graph that I'd thrown Peter, boop, 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 can box counting get us the same answer? 1, 2, 3, 4. Sure as heck can. All right. So, variety of methods to get at it, but in the end, hopefully you can kind of get behind the simple idea of box counting to get the displacement. Okay, it went 2 meters every second for 1 second. That'll get you 2 meters. Then it went 1 meter every second for 2 seconds. That'll get you a further 2 meters. That gets you 4 in total. Or 1, 2, 3, 4 boxes. Each box is worth 1 meter. Boom. All right. I'm gonna get crafty here. So give me a second. Let's see. Oh, that's poor. Let's see what I can do with this. There we go. All right. I'm going to do this so that I can do this. All right. Back to this. Now what's your answer? How does the displacement of object 1 compare to the displacement of object 2? Object 1 has a displacement which is greater than object 2, equal to object 2, less than object 2. Whoa. Haha, I'm going to lock it out there. Just because oh man, it was even, and then some donkeys moved their votes. Pretty close to even. 12 to 10 right now. 12 people think object 1's displacement is greater than object 2. 10 people think that object 1's displacement is less than object 2. So run that by your neighbor real quick. All right, let's see how convincing your neighbors were. Quick revote. Greater displacement. Object 2, object 1. Or I should say object 1's displacement is greater than object 2's COP. All right, let's just throw to this answer because Boop. There we go. So, yeah, what do you think the displacement of object 2 is? Poop. Aye, stinky pants. Let's figure this out. Alright. Boop. Alright. So we've got a fair few threes, a fair few sevens, a smattering of ones, and then a shout for 5 and a shout for 11 there. Okay. So 3 and 7 appear to be the most popular option. Nobody had 9. That would have been another one I would have expected, but I don't see it. So take a look at this 3 or 7. Think about how those might happen on here, and reference that with your neighbor. So I guess the most important thing would be to, if you're a 3, can you see how somebody got 7 from this? If you're a 7, can you see how somebody got 3 from this? Because there are a lot of people getting those answers. All right. Nobody said 9. Man, that blows my mind. 1, 2, 3, 4, 5, 6, 7, 8, 9. I see 9 boxes. Okay.
Yeah, man.
Now, I think that comes from a strict mathematics definition of what we said there, which is the area under the graph or area under the curve. Might lead somebody to say 9 boxes. Nobody said that. They said 3 or they said 7. Those are both answers, but they are answers to different questions. Okay? What is 7 meters to this? Because that is the correct answer, but what is that the correct answer to? 7 meters is the what? Run that by your neighbor. Okay? 7 meters, I think, is the step count or total distance. I think in total this object moves 7 meters. But that differs from the displacement. Okay, remember that for us. Oh, I don't like that thick pin. There we go. Boop. Displacement is the area between the graph and the x-axis. Okay, so the really important bits of this, the x-axis. That needs to be one of the first things you do when you're looking at one of these velocity time graph problems, is try to very clearly establish the x-axis. Okay, it goes through at 0, 0. And then the next important terminology here is between. I want to only focus in on the areas that are between that graph and the x-axis. Mr. Harding, I think if you count those boxes, you'll see you have 1, 2, 3, 4, 5, 6, 7 boxes, you donkey. Okay, fair enough. But what that's not taking into account is the area of this box right here. This box, if I can pull that out, boop. That goes from 0 to -1. So this side is -1 meter per second. The bottom of it is 1 second. So then I would say -1 meter per second times 1 second equals -1 meter. The boxes below the axis count as negative. The boxes above the axis count as positive. So in the end, I have 5 plus -2 equals 3 meters. That would be the displacement of object 2. Okay? So proceed with caution there. You have to pay careful attention to where the x-axis is. And this is why I prefer the word between to below or under. Okay? Because we're only looking for the boxes that are bounded by the graph and the x-axis. And that's how I get 3 meters for the displacement. Okay? Let's take that to the boards. Let's see here. Tatiana? Boom, there you go. Pick a board, any board. All right, the arm is warm now, so let's have at it. Are you sure you're left hand? There we go. Got it. Go into it. Yeah. Hi. This group, come on up. Have at us. We're going to start friction in the neighborhood. Talk to us about how you got from the position versus time graph to the velocity versus time graph that we see there.
So it starts off at 0 here, and then you see that it starts off at 2, and then travels 1 meter. That's right there. Travels 1 meter forward, then travels back to 2, down here, then back to 0.
So how do you get that from the position time graph? How do you know where the time?
Because the position over here started at 2, and then it was plus 1 velocity, which means it's going 1 per second, and then since it's 1 per second, it went over 1 second, and then again the next second it went over 1 velocity, so 1, which means it's going up another 1, and then it went to -2 velocity, so then it had to go back to per second, and then it went back.
Okay. So you said on the position versus time graph, prior to 2 seconds, the slope is. Prior to 2 seconds, the slope on the position time graph is 1 meter per second, and then after 2 seconds, the slope is. Okay. So that's how we know which levels to set those at. And then then it's onto the motion map. Why don't you go ahead and flip another board and let's hear what they did with their motion map, right? 'Cause we haven't talked about how to do motion maps, so there's going to be a lot of variety here. That's good.
I don't know.
'Cause how many you guys had? How many dots on yours?
4.
I counted 6 dots.
5.
Okay. This group has maybe 4. All right. So coming up and talking about your motion map, what do you do? Okay, go for it. Have Marcus is right there by you. Okay.
So the object started at zero. It took 1 second to come. So that'll be about 9 to 12. From there, it goes in the opposite direction. From 4 meters back to 2 meters. And then from 2 meters back to 0 meters.
So in that way, what is the longer arrows in the second part of the motion telling us? Okay. So the length of the arrow in the motion map can kind of communicate about relative velocity. Okay. How many dots do you now have? 4. Okay. Can you put a tip on that arrow? Yeah, there we go. Okay. It's kind of hard to tell. Like most groups kind of did this where they made the arrow like fill in the gap. Okay. That makes it a little tough to see the dots sometimes. Are we ever at a position of 0? So at what time would that be that we're at a position of 0? Yeah. So I'd go ahead and throw a dot on there. And so this is where the question of how many dots kind of comes into play. At what time are we at 2 meters? Okay, fair enough. We're there twice. We're there at 0 and at 3 seconds. So we are at 2 meters at time 0. Then we are at 3 meters when the clock reads 1 second. We are at 4 meters when the clock reads 2 seconds. We're back to 2 meters when the clock reads 3 seconds. And then we're at 0 when the clock reads 4 seconds. So it seems like we should have 5 dots. It looks, is that what you have now? Okay. So really important is that they only have 1 dot at the 4 meter mark. Okay, they don't want to put a dot with that lower row of arrows because then that would imply that it's staying there for a second. Okay, so that's kind of the funky things about motion maps is recognizing that the clock starts with 0. Okay, you're not born 1 year old, right? You're born 0 and then you got to go around the sun once before you're 1. So to help people recognize the other issue too, like when you're looking at these, it looks like they both started and then they went up to the next level, but sometimes people like to start up top and like work their way down the page. To indicate the initial dot, go ahead and put a circle around your first dot, right? And that circle is a 0. That coincides with time 0. So it's perfect. Now we know that's where that motion map starts. Starts at 2 meters, and it's 0, so 1, 2, 3, 4 seconds. You kind of work it that way. We're just learning about motion maps. I would encourage you to leave a little bit of space. Don't make the arrow fill in the whole gap because there'll be some times where we do have changing velocities, and so you're going to want to have a little bit of room there. If you're not as great at drawing arrows as this group is, another thing that you could do to show those first two arrows are the same length is put a little tick mark in there. So if you want to go ahead and do that, put one tick mark on those lower arrows, and then if we put two on the uppers, then we know those two are the same but longer, and like they said earlier, that coincides with velocity. So that's more than you ever needed to know about motion maps, right? But when we deal with more complex motions, sometimes they're helpful. We saw some real life examples of them. All right, cool. And let's see, so that's the motion map. I'll go ahead and flip another board to talk to us about CI. CI. All right, that group. What should our first grouping theme be when we actually name the groups? We need a suggestion box. What do you think? Harry Potter groups? You want to be Hufflepuff?
No, it's not enough.
It's not enough. No.
Yeah.
Musicals?
No.
That could be kind of fun.
Yeah.
Like you can't be LeBron James, that's one person, but you could be the cast of Hamilton. And then you would have to like spit bars and like a Lin-Manuel Miranda cadence every time you presented. I think that would be kind of cool. Be like Schmigadoon for life being musical. It'd be great. Alright. So on the velocity versus time graph, shaded area between the lines of horizontal axis between 0 and 2 seconds, fills area between 2 and 4 seconds. Calculate the shaded area, show your work units and all numbers in your calculation. So I think you did that. What'd you get for those areas?
So here in this block, we have this would be 2, and here on this block would be -4. And so when you add 2 and -4 together, you're going to get -2. Your units for this should be, if you're taking meters per second times second, the second should cancel out. You should just get meters.
Fair enough. Were you gaming us? Is that what you were doing? They won't tell. Secret light. Yeah. So just next time, just plow right through what that means for a second. See if one of these quiet people will ask you a question about it. So okay. So you're saying the displacement then is -2 meters. Can you reconcile that with what the position time graph is showing us?
Here. So we just do this for reference. So we're starting at 2 at time 0, and we end at time 4 at position 0. So we're 2 down from where we originally started, -2.
Excellent. Okay. So initial position is 2, final position is 0. The overall change in position is -2. We're showing how, and I probably need to add that to that. We're showing how these things are consistent. Displacement is the area between the graph and the x-axis. It also is the change in position, the final position minus the initial position. And they're getting consistent answers there, -2 meters. All right. And then, yeah, same deal with the motion map, right? See how the change in position is -2. Go ahead and flip another board to talk to us about D. Got it. We'll get there. All right. And I should mention too. So it seems like it's pretty natural for everybody to represent velocity with an arrow, and that's usually what these mean on here. We could also represent displacement as an arrow, and we don't do that much until much later on in the year where we talk about specific arrows to represent position. But I could draw one arrow starting at 2 and going to 0, and usually I would make that like a thicker arrow of sorts. And that can represent the total displacement. And that's just drawn from the initial position to the final position, and that lets us know the change in position. It doesn't tell us very much though about what happened in between. Okay. But if I wanted average velocity, I'd go for that focus. Right. Do the results of this problem change your view of what the shaded area are? Mathematicians use the phrase. I like how haughty this worksheet seems to be about mathematicians. Mathematicians use the phrase area under the curve to somewhat inaccurately describe the operation of finding the area between whether that's above or below the line on the graph, whether it's straight or curved, and the horizontal axis, regardless of what so when we look at our process that we're using these graphs, in what ways is this similar to finding the area of what you're doing? Okay, so we're taking width, we're taking length, two-dimensional space, just like when we're finding an area. And then in what ways would we say this differs now, especially after today? What the hell is that? Is anybody in that math class? That's got to be like year 4 over at the U or something like that. Okay, we have negative areas. It's probably a thing, right? Who's in differential equations? Some of you probably, right? That's the negative areas. You're not to that chapter yet. Okay, we'll wait for it. So yeah, so that's kind of awkward, and then also the units, right? That it's meters, not meters squared or meters. So super cool. All right, camera. Get a picture of some of these, throw them in the notebook. We were kind of talking about this stuff last hour. Like, if you're not aware, you should have this in Canvas. Like, people were coming up with their Chromebook to take pictures, but the stuff that I'm writing in the class notebook, you should be able to get that in Canvas. If you can't yet, let me know, because you're missing out on all the fun. Notebook. And also, I'm like keeping track of our work here. That way too. So, fun thing. Oh, wow, so cool. I don't know if we already tried this in class too. Then on the Canvas 4 today, I've got a video on the lab that we're going to start tomorrow. And I'm very much saying that with my fingers crossed because apparently you can't access the Chrome Web App Store because they think teenagers would just play video games if they can access the Chrome Web App Store.
Yeah.
Can you check and see how many of you maybe have graphical analysis from last year on your Chromebook or 2 years ago? You got it? Yeah, you got it? Okay.
I think so.
Yeah, if you want to check your Chromebook and see if you already have it, we may still be able to make this thing work. We're just going to have like 5 groups of 7 or something. All right, I lied on that. Might be time for a new phone. All right, cool. Go ahead and send somebody by to clean up your whiteboard, put it back in the clean whiteboard storage.
I don't know if we have to.
All right. You had new Chromebooks last year?
We received them at the end of last year.
Oh, okay. Like this Chromebook, you got it. Yeah. But if during last school year or the year before you used graphical analysis?
Everything is stored on the cloud, so it shouldn't matter.
Yeah. But the kids that
Oh,
didn't
yeah.
have it can't get it.
It's the website where you like plug something in.
Yeah.
I think I still have it.
From like Project Lead the Way or something.
Yeah.
Chemistry, yeah.
Chemistry. Okay.
Chemistry we used it.
Yeah. Oh, you can just use a sock. It's freshing.
Yeah, but it's not coming up.
Not freshing.
We did this yesterday.
Oh no. That elbow grease.
What is it?
Go to like our No. Out of class, it's 15. Yeah.
What's up? Oh, so right by that astronaut picture? Oh, that should be a pile of things.
7 periods starts. Get out of class. Yeah, I'm going to get
Ooh, let's see what they say. Start.